Okay, in this lab, we will study basic buffer overflow attack. We will use a few C programs and some server to demonstrate the scenario of a buffer overflow. The server exposes stack-based buffer overflow vulnerabilities. I'll give you a few demo code to show that the attacker can utilize this vulnerability to make the server run spurious code. So this lab requires a Linux machine as a server. We use a 64-bit Ubuntu 14.04 running on a laptop with Intel processors. So the first task is understand the concept and the importance of a buffer overflow. So most compilers or runtime libraries automatically generate bound check code in debug mode to avoid array index out of range error. So this is a root of a buffer overflow vulnerability. However, for most software in production system, the checks are removed due to performance issues or careless programmers. This is particularly true for C and C++ code. So practically nearly every worm on the internet utilizes some kind of buffer overflow vulnerability to inject code into running executables. Now let's take a look at the call stack layout. Consider the following code, the stack buffer.c code. Here I declared a function called func. It allocates a buffer of 4 bytes and initializes each 4 bytes to 0, 1, 2, and 3. And if we call the function func in the main function, and this piece of code allocates a buffer of 4 integers on stack at compile time, so the size of the buffer is fixed. So buffer overflow may happen when writing information to the buffer allocated on stack while the size of the information exceeds the size of buffer that's holding it. Every time a function is called, a new stack frame will be created. So let's see the following code. Here we define a function also called func. It has 8 parameters, all long integers, which is the same size of a machine word. And this function allocates 4 long integer as a buffer. We will see what is the stack frame looks like. We will printing the starting address of this buffer, and we will print 10 long variables before the starting of this long variable buffer, and 10 long integers after that. So let's run this piece of code. I already coded here. So we'll just inspect the code a little bit and run it. Okay, let's see this buffer stack layout.c. See, and let's compile it. And run it. Now we can see the printed values of the stack frame. Okay, see, this is a return address of the function func, and this is a push the RBP of the function. So after these 2 long integers, these are the buffer allocated and the stack frame allocated for the function. So based on our previous analysis of code, we allocated 4 long integers on the stack. They has value 10, 11, 12, and 13. So in hex decimal it will be A, B, and C, and D. we can see the buffers are allocated on the stack frame of the callee function. And on the left column is the address of the stack. So let's explain this a little bit. What will happen? So when this code is executed, it generates the following output like this. The stack frame of different functions are explicitly marked here, and the stack frame of main and the stack frame of the function func. We can see all the parameters are passed, and not all the parameters. So the first 6 parameters are passed by registers, and the remaining 2 parameters, the 7 and 8. So here when I call the function func, I initialize, give the value of the 8 parameters from 1 to 8. So I can see the last 2 parameters, the 7s and 8s, are passed by stack, and the other parameters are passed using registers. So we can see before calling a function, the return address, this return address, is first pushed into the stack. So also the callee will push the old stack base pointer, which is RBP in our case, to the stack. And the callee will reset the value of a stack base pointer to the value of a stack pointer, which means assign RBP as RSP, and subtract the stack pointer by a certain number value to create a new stack frame. This new stack frame will hold all the local variables. When the function returns, it executes a leave instruction and a return instruction. So the leave instruction will restore the value of a stack base pointer and stack pointer, and the return instruction will return to the place designated by the saved return address on the stack, which is this address. So let's see what it looks like in assembly code. Here's a section of the assembly code of the stack layout.c. We can generate this by compile it with a /s flag, gcc /S stack layout.c and /o stack layout.s. And then let's inspect the assembly code a little bit. So the code is a little bit long. I put it here and highlight the important things. So you can see the function we called as the entry of this function is here. So the first instruction would be push RBP, and then move the value of RSP to RBP, then subtract RSP by a certain value. Here is 96, which is the size of the local variables and also the part of the parameters. So when it returns, it put the return value to RAX register and call leave, and this leave instruction will restore the stack frame, and the return instruction will return to the address saved on the stack. So when is the address saved? When you run this instruction, the call function. So call function is in the main function here, in the main function. First, we can see we put all the parameters, either pass the parameters through registered or pass the parameters through stack. The first 6 of them are passed by registered, and the next 2 will be passed through stack. So if you have more parameters, usually the first 6 of them are passed by EDI, ESI, EDX, ECX, R8, and R9. And the sequence of passing parameters in C is from we can see is from left to right. Okay, so here's what happened on 64-bit x86 machine. So when a function is called, there's a standard called calling convention that makes sure the function, the caller and callee follow the same rules. There are a few rules listed here. First, the stack grows from higher addresses to lower addresses. Two registers are used to access the stack. First, the frame pointer, which is the RBP, base pointer kind of a stack frame base pointer. And the next is a stack pointer, RSP. It points to the top of the stack. So stack frames are usually aligned on 16-byte boundaries because we're running on a 64-bit machine. And the call instruction pushes the address of the next instruction. Here we can see one main function calls func here. The call instruction will push the immediate next instruction, which is an instruction about the position of this printf, and put the call instruction will put this address on the stack, which is this return address. You can see it here. And so after push the return address onto the stack, the control is transferred to the addresses of the function you called. Upon entering, stack frames are initialized with the following sequences: usually push RBP, move RSP to RBP, then subtract a certain value to make room for the local variables. And after the function finishes, the leave instruction set the stack pointer back to frame pointer, and then set the frame pointer to the saved frame pointer. So which means restore the value of RBP. And the return instruction pops the return address of from the stack and jumps to it, so that after the function call you return to the caller. And on x86 64-bit machine, the registers RBP, RBX, and R12 to R15 are saved by the callee. All the other registers are saved by the caller. So arguments are usually passed from left to right in C programming language. The first 6 arguments are passed in registers in the sequence of RDI, RSI, RDX, RCX, R8, and R9. So the remaining arguments are passed by stack using the region just above the return address, from low to high. So remember that the stack actually grows from high address to low address. So let's see the diagram of a general stack layout. The memory argument would be layouted here, just above the saved return address. And next is especially the end of the argument area must be a multiple of 16, which means the area will be padded here. This area will be padded to a multiple of 16 byte. And the function local variables resides on the function's stack frame created at enter. So here you see the callee will subtract the RSP to a certain value to create a room to hold all the local variables. And the return value is usually passed by RAX. If RAX cannot hold the return value would be put here as a outgoing arguments after the local variables. Okay, So now we can see clearly if the function uses a buffer of a byte array declared as a variables, local variables, so the buffer would be allocated somewhere here. And on the callee function's stack frame. So if the buffer array index out of range happens inside this callee function, then it is possible to overwrite the saved RBP register and even further the saved return address or even variables of the previous frames. This may cause unexpected behavior when the callee function returns. Usually if you write some garbage on the return address, you will get a segment fault. We'll see it later. And this creates a vulnerability. Malicious code might use this vulnerability. For example, if the callee function is a socket buffer receiving function and it writes the byte received on this local buffers, and if that function does not check the boundary and this buffer might overflow, then we will write a lot of garbages here, or even the attacker can inject malicious code saved on the buffer of this local variables and overwrite the return address, and this the return address would point to somewhere on the stack, so that when your callee function returns, it will jumps to where the return address points and run the code on the stack. So let's see an example of overrunning the memory allocated on stack. Here I declared a structure. It contains a byte buffer and an integer variable after it. So C programming language forces this kind of structure must be layouted in memory in the same sequence as it is declared. So there will be 4 bytes, and after the 4 byte toward the high memory address, there will be another 4 byte of an integer. So let's see, we created a get hex character function to read a hex character and interpret it as a byte, and we will use this function to receive some input, and we will carefully construct the input to overwrite this buffer. You will see initially we declare the buffer B and assign this. We didn't initialize it. So we initialize it. We initialize b.var as 0. We'll see after this is executed, the buffer would be overwritten. So I put the code here. Let's compile it. It's called buffer overrun.c. Okay, let's run it. So it asks you to input something. I list the input here. Let's see. I input 0, 0, 1, 0, 2, 0, 3, 0, 4, and 0, 0. Here we use 0, 0 as a denote of when to stop to receive the input. So I put 0, 1, 0, 2, 0, 3, 0, 4, 0, 0. So what does this program do is we receive 4 bytes and write this 4 byte to the structure b.buffer. Remember that b.buffer can only hold 4 bytes. It can only hold 4 bytes. Now we received only 4 bytes. It's okay. The buffer does not overflow. So let's try again. You see, if the buffer is not overwritten, the b.var, which is a integer immediately after this character buffer, is not changed. Previously we initialized it to 0. Now it is unchanged. which is a expected behavior. However, what if I write 0, 1, 0, 2, 0, 3, 0, 4, 0, 5 and 0, 0 to terminate it? Let's try it again. See, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. You can see, even though in the code we never assign b.var, and b.var is overwritten to 5, which means the memory that holds this variable is just after this 4-byte array, 4-byte array as a buffer. So when receiving characters and writing to the buffer, if we didn't program very carefully here, we didn't check whether the number and the value of I exceeds 3. So if I exceeds 3, it will overwrite the memory after this 4-byte buffer, which is the memory that holds this var, and var will be overwritten to some value unexpected. Here it is the next byte, we write it to 05. Okay, this example illustrates the basic idea of overrun the memory buffer. If we just overrun the memory buffer, it is okay. Next, we'll try to craft some input to exploit the buffer overflow vulnerability, which means we are gonna overrun the buffer and rewrite the return address so that spurious function will be called. So refer to the previous two tasks, and now we know the stack frame layout and how to overrun the buffer. And the attacker usually deliberately overrun the buffer so as to change critical data, usually the saved EBP, RBP, and the return address. RBP instead of EBP because we're running on 64-bit machines. The following code is used to demonstrate the misbehavior of the program and the buffer overflow vulnerabilities. So this is a combination of task 2 and task 3. First, we still need this get hex char function to receive input and construct bytes from the keyboard. Next, I define a macro to print out the stack frame layout, the same as first task. Next, we put the function modify the version of the first task here, and allocated a buffer of 2 long integer. And now we are receiving bytes, and write these received bytes to the buffer of 2 long integers. 2 long integer on 64-bit machine is 32 byte, because no, not 32 byte, 16 byte, because 1 long integer is 8 byte. Okay, then here's a function, the surprise function. We can see through the whole piece of a code, we never call this surprise function. And at the beginning, we print out the address of this surprise function, and we carefully construct an input that makes a program overrun this buffer, and after the func returns, we will call this surprise function to create a spurious behavior. So let's run this code. The code is called buffer overflow. Let's compile it. Okay, let's run the buffer overflow. So first, it prints the stack frame before we modify anything. So the address of a surprise function is here, like this. So we can see the stack frame of a callee function, the func is like this. This is a stack frame of a main function. Okay, let's carefully construct a few inputs like this. We will put a 16 1, 16 2, 16 3, and 16 4, and end with 0. So I'm not gonna to input this long string. I will just copy and paste. See here, let's copy and paste, and bingo. You see the program exit on exceptions as segment fault, and after it receives these long input, it prints out the stack layout. We can see here in our program we declared the buffer of that hold two long integers. It is initially 10 and 11. Let's find it on this buffer. So 10 and 11 would be A and B. Okay, so as we said, local variables will reside on the callee function's stack frame. It is here. This is a first long variable, and this is next long variable. Remember that stack grows from high address to low address. Okay, see, the next line says we are receiving bytes and write these bytes to the buffer of the two long integer. The two long integers are 16 byte. Now we write 32 byte in total. Yeah, so two characters are 1 byte in hex. So we are writing hex value 11 as the first byte, 11 as the next byte, and we write 11 for 8 byte, 22 for 8 byte, 33 for 8 byte, and 44 for 8 byte. So we can see the first 8 byte will be written on the buffer that holds the first long integer here, and we did change it to all 1. The next, we will write the all 2 on this, the buffer hold the next long integer, and we did write all 2 here. However, the next 8 byte would overwrite the saved RBP. See, the saved RBP are changed to all 3, just as what we input. And similarly, the saved return address will be changed to all 4. So return address will be changed to all 4. So after the callee function returns, it went to this address. However, this address does not contain any valid code, or even the operating system kernel does not map any memory for this address. So we got a memory violation, and the program is terminated, printing out a segment fault. Let's do a little bit analysis. So basically, we overrun the buffer here. We overrun the buffer of long variable here, the buffer that can hold only 16 byte. We put 32 byte, and so these buffer overflow, the consequences of this buffer overflow is RBP is changed to some input value, and return address, the saved return address, is also changed to some value we input. And now you can see we can change the return address. These outputs are just up to here, and listed also in the tutorial document. So now we can see that these saved RBP and return address can be changed to some input value. How about we change it to some entry address of a function, like the surprise function? Let's do this experiment. Okay, this time we will input all 1 for the first 8 byte, all 2 for the next 8 byte, all 3 for the next 8 byte, and the address of the surprise function here. Note that if we print an address here, the most significant bit would be on the left side. But when inputting on the command line, we are input 1 byte at a time. So these numbers will be 1 byte denoted by 35, another 1 byte denoted by 08, and another byte will denote by 40. So we'll put these 8 byte here. Now all the other bytes are 0. So let's use this input and see what will happen. See, paste, and bingo, you can see the surprise function has been called. So if we go over this piece of code, we never call the surprise function, but the surprise function is called unexpected. So let's analyze a little bit of what happened here. Previously, we can see we can overwrite the saved return address to the input value, which is the last 8 byte, not last 8 byte, the first 8 byte, next 8 byte, and third 8 byte, and the fourth 8 byte here. We overwrite the return address to all 4. So here we just change the value to a valid address, which is this address. At the beginning, we print out the entry address of the surprise function. So if we put it here, this means the return address of the callee function will be overwritten as the entry address of the surprise function. When the callee function returns, it does not return to main function. Instead, it returns to the surprise function, which makes the surprise function being called spuriously and print out this surprise. However, after that, surprise function should return, and by return it restore the saved RBP and clean the stack and do a little bit of this kind of stuff and retrieve the saved RBP that the surprise function assumes, which is here, and retrieve the saved return address that the surprise function assumes that would be pushed on the stack, which is here. Then the surprise function will return to this address, which is not a valid address, and the kernel will terminate our program and print out a segment fault. So this basically an illustration of how we can deliberately construct an input to change the return address of the callee function so that we can return to another place. Here the other place is some function we coded in our program. It is completely possible that the attacker will inject a few runnable code here on the stack in this buffer and modify this return address to point into the malicious code on the reside inside the buffer that is allocated on the stack. So then the attacker is able to run the injected malicious code and corrupt the system. So let's discuss a little bit how to prevent this kind of buffer overflow vulnerability. C and C++ provide no built-in protection against accessing or overwriting data in any part of the memory, and do not automatically check that data written to an array is within the boundary of that array. So instead, Java and Python check this. So this makes the C and C++ program suffers from buffer overflow attack more easily. Bound checking can prevent buffer overflows. So this means the programmer needs to check the boundary every time manually. For example, if when I putting a character received to a buffer, I always check whether I run over this buffer first by comparing the array index with the size of the buffer. So in this way we can prevent the buffer overflow vulnerability. However, we need to manually change every time we want to use a buffer, and this buffer every time we want to receive something from network or from a file from a keyboard input. So in large projects, just one negligence of bound checking will create a break of a buffer overflow vulnerability. Okay, so that's it. A straightforward demonstration of a classical buffer overflow attack. I made all the tutorial and all the code myself, so we'll share it in the video also online. So have a good time, play with it. Thank you.